in the form of an example. Okay. So, the example is number 3 here. So, the example I have is that of the Lagrangian for the Kepler's problem. Okay. So, for the Kepler's problem, my Lagrangian is as follows: L of t comma q bar dot, which is m by 2 q1 dot square plus q2 dot square plus k by square root q1 square plus q2 square, right. Okay. Where my m is positive and k is a constant, right. So, these are my, this is my setup. So, now I have to set up my well, let me call this as condition 1 prime. So, I have to set up my condition 1 prime to find the infinitesimal generators, right. So, in this case, so we have to find xi comma eta 1 comma eta 2, right, my infinitesimal generators for the variational symmetry. So, again, to set up the prolongation operator, let us calculate some of these partial derivatives. So, del L del t, note that L is independent of t, the independent variable. So, this is 0, and then my generalized momenta p k is del L del q k dot, this is also equal to differentiating m q k dot, and also my other derivatives, partial derivatives, del L del q k is the only place where q appears is in this potential energy, k divided by square root of this quantity. So, I get that this is also equal to negative q k times k divided by q1 square plus q2 square to the power 3 by 2, right. Okay. So, my prolongation operator in this case, PR1 of VL is equal to eta 1 del L del Q1 plus P1 times eta 1 minus xi 1 Q1 plus eta 2 times del L del Q2, this is a 2D problem, plus P2 times eta 2 dot minus xi dot q2 dot. Okay. So, I plug in all these quantities. So, let me plug in all the quantities and write down the expression. So, after plugging in all the quantities, I am going to get the following expression. This is quite long: eta 1 q1 plus eta 2 q2 divided by q1 square plus q2 square to the power 3 by 2 plus m times eta 1 dot q1 dot minus xi dot q1 dot square plus eta 2 dot q2 dot minus xi dot q2 dot square. So, these are my first set of terms, and then plus m times terms like negative q1 dot cube xi 1. So, xi 1 is the derivative of xi with respect to q1, right, minus the next term q1, okay, minus the next term is q1 q2 dot cube xi 2, and again this is the derivative of xi with respect to the variable q2, okay, minus q1 dot square q2 dot xi 2 minus q1 dot q2 dot square xi 1 plus q1 dot square eta 1 1 minus xi t, where eta 1 1 is the derivative of eta with respect to q1, right. So, eta 1 1 is the derivative of eta 1 with respect to q1, okay, and then this is well, the other set of terms is q2 dot. So, the reason I am writing is for all the students to go home and check that we indeed get all these terms minus xi t. So, again eta 2 comma 2 implies partial eta 2 partial q2, okay, and then plus q1 dot q2 dot of eta 1 comma 2, and the notation is obvious, plus eta 2 comma 1 plus q1 dot eta 1 comma t plus q2 dot eta 2 comma t. Okay. So, I am done with writing all the expressions. There is one more expression that I need to write, and that is, so we have right now written what is the prolongation, first order prolongation operator for L, the Lagrangian, and then we also need to check what is L xi dot. This is also equal to m by 2. Well, so let me write down after multiplication. I get the following terms: m by 2 q1 dot cube xi 1 plus q2 dot cube xi 2 plus q1 dot square q2 dot xi 2, and then plus q1 dot q2 dot square xi 1 plus q1 dot square xi t plus q2 dot square xi t, right. Okay. So, k plus k by square root q1 square plus q2 square times xi t plus q1 dot xi 1 plus q2 dot xi 2. Okay. So, these are all the sets of equations that we are going to get. So, I am going to term this gigantic expression as A and this as B. So, I have to add A plus B and equate the various powers of q1 dot and q2 dot, and I am going to get the following relations. So, A plus B set equal to 0 implies, let me now go to the next slide. We are going to get the following set of relations by equating various powers of qi dot. The relations I get is eta 1 comma 1 minus xi t by 2, this is 0, and eta 2 comma 2 plus minus xi t by 2 is equal to 0, plus the third the third relation is eta 1 comma 2 plus eta 2 comma 1 is equal to 0, and I also get eta 1 comma t is equal to 0 and eta 2 comma t is equal to 0, and finally the relation q1 square plus q2 square of psi t minus eta 1 q1 plus eta 2 q2 set equal to 0. So, let me call this as expression A, this as expression B, expression C, D, E, and finally expression F. Okay. So, from A, also let us go back few slides. Notice that in A we have coefficients of the form q, we have terms of the form q1 dot cube, q2 dot cube. Now, all these coefficients, the coefficients of these cubic terms, they will vanish. So, xi 1 is 0 and xi 2 is 0, right. So, from A we see that coefficients of q1 dot cube and q2 dot cube are 0, or what I get is xi 1 is xi 2 is 0, or I get that xi is purely a function of t, right. And then, so it is purely a function of t. So, then from these two relations I also see that eta 1 and eta 2 are independent of the variable time, right. So, from D and E I see that each of these etas are just functions of the respective just functions of the dependent variable q, right. So, let me call this relation as G. Now, from A, B, from the first two relations and G, so from A, B and the relation G, what I get is as following. It turns out, notice that we are equating eta 1 1 is nothing but the derivative of eta 1 with respect to q 1, and xi t will be purely a function of the independent variable t, and we are equating these two together, which means that both of them, this quantity and this quantity, both of them must be constant. So, which means we conclude that there exists a C1, there exists a C1, a constant such that xi t is equal to 2 C1 and eta 1 1 is equal to eta 2 2 is equal to C1. Okay. So, from here we can conclude several things. Well, first of all, psi must be a straight line, right, and we can continue, but most important, notice this relation. So, from that relation I can immediately get that eta 1 is C1 q1 plus g of q2. If you differentiate with respect to q1, I get C1, and eta 2 is C1 q2 plus, let us say, h of q1, right. So, then if I were to use another relation, let us say C, this particular relation, I can conclude further. If I were to use relation C, I see that del G del q2 is equal plus del h del q1. Well, one is a function of q2, the other is a function of q1, both equated to 0, implies both are constants, implies del G del q2 is equal to negative del h del q1, which is equal to C2, right. So, I get so I get the following. So, I can integrate this relation, and from here I get that eta 1 is C1 q1 plus C2 q2. So, this is a straight line with respect to the variables q1 and q2 plus C3, and eta 2 is C1 q2 minus C2 q1 plus C4, right. Let me call this. So, this is a straight line. Finally, if I use my condition F, my condition F is, I plug in the last relation, I see that C1 q1 square plus q2 square minus C3 q1 minus C4 q2 is equal to 0, and if I were to equate this, I get that C1 is equal to C3 is equal to C4 is equal to 0. So, this is gone, and this is gone as well, right. So, all I get is that eta 1 is C2 q2 and eta 2 is minus C2 q1, right. And finally, we can also, from all these observations, we can also get that xi, which was originally we found to be a function of t, comes out to be purely a constant. Okay. So, that comes from that comes from this these set of relations that we have been using. So, students should check that. So, what is the conclusion here? Notice that the way the infinitesimal generators are found, this is nothing but the rotational generators, right. So, eta 1 depends on q2, eta 2 depends on q1, provided this constant C1 C2 is non-zero, right. So, the conclusion is we have two parameter family of variational symmetry. So, what have we got is that if my C2 is 0 and C5 is not 0, if C2 is 0 and C5 is not 0, well, I can only get a time translational symmetry, there is no rotation, right. So, this is time translation or translation in t. Now, on the other hand, if C2 is not 0 and C5 is 0, then I have a pure rotational transformation, right. So, what have we found? that in the Kepler's problem, the only variational symmetries are linear combination of rotation and time translation. Okay. So, we end our topic, our discussion by concluding that we can continue finding these variational symmetries for functionals containing integrand of higher order derivatives in a similar fashion. So, let me write down the result for functionals containing higher derivatives let us say up to nth order. For functionals containing higher derivatives, let us say up to nth order, right. We calculate higher prolongation. We call this as PRN of VL. Well, it is easier said than done. As we increase this n, as n becomes larger and larger, this becomes quite complicated to find. Okay. So, I am not going to write the general form, but again I will end the discussion by mentioning what is the condition for existence of variational symmetries with, in this case, existence of variational symmetry is this particular differential equation that needs to be satisfied. The nth order prolongation plus L times xi dot is equal to 0. So, that is along the similar lines for functions of one dependent variable, okay, or functions with just first order derivatives. Okay. So, that completes our discussion on finding the necessary condition for the extrema of a functional. I am now going to shift my attention to calculate the second variation, or to look at the sufficient condition for an extrema, for the existence of the extrema. Namely, if the extrema that we found, whether it is a maxima or a minima. Okay. So, we start our discussion on the second variation. So, the idea is, why is second variation the topic is important? Because so far we have looked at the various forms of Euler-Lagrange, but Euler-Lagrange only provides the necessary condition for the existence of the extrema. It does not provide the sufficient condition. Okay. So, it only provides the necessary condition for the functional to have an extremum. Okay. And this is similar to my first derivative. Or my gradient test in infinite dimensional space Rn, and Euler-Lagrange is, well, it is not a sufficient condition, as I just said. So, not a sufficient condition, and especially to determine the nature of the extrema that we find. Okay. So, or this statement is equivalent to saying that a vanishing first derivative in the finite dimensional calculus or the first derivative in the finite dimensional calculus set equal to 0 is not a sufficient condition for the extrema. Okay. So, vanishing first derivative not a sufficient condition for the extrema, right, in Rn. Okay. So, then we are going to investigate. So, which means the moment the Euler-Lagrange does not provide us with the sufficient condition, the natural idea is to look for the higher order terms in our variation of the functional. So, we are going to look at the terms of the order of del square j. So, the idea is we need to investigate next term next term in the expansion of j of y hat, well, j of y hat minus j of y, right, the variation, which will be our second variation of the functional, right. Okay, so this is my second variation, right. Okay, why, what is the importance of the second variation? Because we will see that investigating the second variation will not only provide us with a more refined necessary condition for the existence of extrema, it will also provide us with the sufficient condition for specific cases. So, it provides us with more refined necessary condition for local extrema, and it also provides me the sufficient condition for y to be a local extrema of j, right. Okay. So, all these statements that I am making for the functional, I am just writing down the equivalent statement in the finite dimensional calculus. So, as if our multivariate calculus is the guiding topic in finding the sign of these or in investigating the second variation. So, let us now briefly touch upon the topics in multivariate calculus related to related to the second derivative test. So, I am going to revisit our concepts in finite dimensional calculus related to the second derivative tests. Okay. So, we will revisit finite dimensional case, we will revisit finite dimensional case in R2. Okay. So, let us consider a function f from omega to R2, which is a smooth, let us consider this to be a smooth function, and let x be x1 x2, let us say x is the extrema, and let us consider the perturbation in x. So, the perturbation in x is said to be x bar plus epsilon eta, where epsilon is positive and my eta is the perturbation vector eta 1 eta 2, this is in R2, right. So, I can expand my smooth function using Taylor series about the point x bar, about let us say some known point x bar. So, using Taylor series, I see that f of x bar is equal to f of x bar is equal to f of x hat plus epsilon times eta 1 partial f partial x1, this is evaluated at x bar, plus eta 2 partial f partial x2 evaluated at x bar, okay, plus epsilon square by 2. The second order terms involve the following derivatives: eta 1 square del f2 del 2f del x1 square plus 2 eta 1 eta 2 del 2f del x1 del x2 plus eta 2 square partial 2 partial f del x2 del x2 square. Okay. So, these are all my terms in the second for the second derivatives, all order epsilon square terms plus order epsilon cube terms, right, which we ignore. So, then suppose, so let me write down this expansion in a shorthand notation, assuming that x bar is an extrema. Okay. So, what we are assuming is, suppose f is stationary or it has an extrema at the point x bar, right. So, then it means that the gradient of f evaluated at x bar will be 0, or my linear term or order epsilon term in my Taylor series is set equal to 0, right. Can we set equal to 0? Because this is nothing but the inner product of eta with grad f, right. When grad f is 0, this term will be 0. So in that case, my f of x bar hat, the perturbed value, comes out to be f of x bar plus the order epsilon square terms, order epsilon square by 2 q of eta plus order epsilon cube term, where my function q of eta is the following quantity. Q of eta is equal to eta 1 square del 2 f x bar del x 1 square plus 2 eta 1 eta 2 del 2 f x bar del x 1 x 2 plus eta 2 square del 2 f x bar del x 2 square. Okay. So, what have we got here? So, we see that for epsilon small, the nature of the extrema will be completely determined by the sign of this function q eta, right. So, what I said is, for epsilon small, the nature of the stationary point, let us say max or min, will be completely determined. Students should note that we are in this finite dimensional calculus, whatever results we are saying it without proof, because the assumption is the students who are taking this course, they have a background in vector calculus. So, they are requested to refer standard textbooks, and we will see that all these results we state in vector calculus will have almost a parallel in functional calculus. Okay. So, this is the max or min is determined by the sign, by the lowest order non-zero, derivative, right, at x bar. Okay. So, lowest, that is the sign of q of eta, right. Okay. Okay. So, it is all about finding the sign of q and how does it change. Now, it turns out, since q is a function, it is a continuous function of eta, we need to check where the sign of q changes. Well, so if since q is a function which is a continuous function of this vector eta, and q changes sign, which means that there will be a value of this function eta where q of eta is 0, right. So, those are the points that we need to evaluate. So, what I said is, since q is a continuous function of eta and q changes sign, right, q changes sign, it implies that there exists a value or there exists a function eta which is not 0, such that so this is a function of a vector such that q of eta is 0, right, which means that, so this is our q. So, our q is this. So, let us set it equal to 0, or let me write it in another form. So, which means there exists a real solution for, notice that this expression q of eta is quadratic in eta 1 as well as eta 2. So, there exists a real solution for the expression eta 1 by eta 2 square, del f del 2 f by del x1 2 plus 2 eta 1 by eta 2 times del 2 f by del x1 del x2 plus del 2 f del x2 the second derivative with respect to x2 set equal to 0. So, this is a quadratic equation for the unknown eta 1 by eta 2, right. So, which means then we have to worry about the discriminant and see how the discriminant changes sign from here. So, standard arguments in quadratic equation. So, which means we have to, so the nature of the solution given by eta 1 eta 2 is determined by, the nature of the solution is determined by this discriminant, which is del f del x1 del 2 f del x2 minus del 2 f del x1 del x2, right. This is set equal to whole square. I call this delta to be my discriminant, right. This is the standard quadratic equation solution theory. So, the theory says, again we are just recalling, if my discriminant is negative, we are in trouble, we will not have a real solution, and further one of the derivatives are non-zero. Further, either del, the second derivative of f with respect to x1 is non-zero, or partial to partial x2 is non-zero, right, at x bar. So, I see that this is a case where q is indefinite, we will not get a real solution for eta 1 eta 2, and the conclusion in the terms of the extremum is that in this situation x bar cannot be an extremum, extremum, since the difference of f of x hat minus f of x depends on the choice of eta, right, depends on the choice of the function eta. Okay. So, in this case my x is also known as the saddle point. Okay. Okay. So, then the case that we are after is when the discriminant is positive. So, which means that if the discriminant is positive, we will have we expect that there will be no real solution to the quadratic equation. So, it is the other way. Yeah. So, if the discriminant is positive, we expect that there is no real solution. So, there is no real solution to the quadratic equation, right, quadratic equation given by q of eta equal to 0, and in that case and so which means the following, which means that q cannot change signs, and in other words I say that q is definite, and let us say, so, and the conclusion from here is that x is a local extremum, and further we can conclude few more results from this, that this local extremum is maximum if one of the derivatives, second derivatives of f with respect to either x1 or x2 are negative, and it is a local minimum if those derivatives are positive, right.